Hey, what's going on, everybody? Man, it has been really interesting talking to you guys. Um, the last couple of videos were pretty successful, so just thank you so much for that, for the conversations. Um, but yeah, let's kind of recap. This is our last episode of mathematics in general, and I only plan on doing about 4 episodes that are long like this, just to give a basis for, I don't know, what we could make the community about. But basically, if you're just joining, or if this is your first video that you're watching, in chapter 0, we performed kind of this number, or we performed this miracle, right? We built a beautiful, you know, way of thinking about the number line, about logic, about what it means to prove something, about all of that stuff. Okay, and then in chapter 1, we learned how to measure that number line. We built the continuum. We mastered, basically, we have like a microscope, right, of analysis to define limits, derivatives, as these kind of linear maps, right? Now you understand what a linear map is, and integrals, right, in terms of like measurable functions, okay, function spaces, which are really just vector spaces. Okay. um in chapter 2, again, we really built the structure, for like, we don't really have to think about vectors in terms of like coordinates anymore, right? We have Lie groups to describe, ways that we transform those vectors to preserve particular symmetries. And then we also constructed tensors and a very special bilinear map, which a bilinear map is the product of two vector spaces, mapping something. And we discovered something called the symplectic form, and then we built basically the bricks of math and physics, in kind of a very unified way. But for right now, our architecture is really boring. Okay, what we have so far has been pretty boring and not that involved, because our spaces have been flat, and a vector space will look exactly the same at the origin as it does a million miles away, in what we previously constructed. So we extend infinitely straight lines across to infinity, and then the Lie group again also has a uniform perfect symmetry associated with it, right? But the real world is not flat. It bends, it twists, it tears, it has holes. Gravity is curvature, right? So curvature is like a more really, it's metaphysics. I mean, it's not even physics anymore. When you think about gravity in terms of the curvature of some abstract geometric space, like, you're not doing physics. You're doing metaphysics, and you're thinking about forces, in a more second order way, right? That's what metaphysics is. It's second order, kth order physics, right? But quantum fields also, these things live on twisted bundles. All right, so that's what we're going to get into in this episode. So to understand the physical universe, we really can't just study, the bricks that make it up, right? We've constructed. We've constructed the objects, which are the bricks, but we also need to construct. We need to study the shape of the building itself to really understand that. And chapter 3, really, geometry and representation, is going to be the study of shape. So we're first going to liberate space, and we're going to allow our coordinate systems to warp themselves. So instead of having, a straight, let's say I have just a basic idea of what a bundle is. Because if I'm talking about bundles, right, my name is, or my alias is Jet Bundle, right? So, if I have two bundles, what does that mean? Well, it's a generalized way of just constructing a coordinate system. So, if I have a line, an infinite line, or array, or a segment, just basic analytic geometry. Sorry, not analytic geometry. Just arrays, Euclidean objects, or whatever. I can then, construct fibers or different ways to shape the coordinate system itself, if that makes sense. So, we're going to discover basically that there are some local rules to creating these coordinate systems. Okay, they're like laws, of calculus or complex analysis, right? They can force global consequences on spaces like this. So we'll see here that space is not just like a static kind of container where things happen, but really it's a container, or it's really a dynamic object itself, right? The space itself is changing, and it's encoded by functions, functions that live upon it. All right. So we're going to build geometry and representation theory at the end, but general geometry, we have to build it in terms of the more intuitive things, and kind of go more abstract. All right, so for general topology, again, we're going to start with the rubber sheet analogy. If you've ever gone to like an astronomy demonstration or something where they're like, by the way, orbits and stuff can be explained by, I'm going to put this bowling ball in the middle of this rubber sheet, and then I'm going to throw a ball, and it's going to follow the curvature of that, and woo, gravity, that's Einstein's idea, woo, but basically we're going to start with this rubber sheet, and instead we're going to throw away the concept really of distance, and we don't care about miles or meters or how to measure things. In fact, we're just going to care about nearness and connectivity, like basic properties of that rubber sheet, right? And we want to learn how to detect holes in the space as well, using basically just using loops, which are called the fundamental group. Okay, and then next we're going to talk about smooth manifolds and Rham Cohomology. So this just allows us to bring calculus back and act on topologies with calculus. We'll define spaces that will look flat when you zoom in, like the Earth looks flat to a human, and this is essentially, it's because of this, but the Earth, of course, is curved globally, right? Even though it looks flat locally. And it's this concept that flat earthers really struggle with. But this allows us to do physics on spheres and donuts and space-time itself. And so we can truly understand the topology, mathematical topology of the world from an intuitive sense, with smooth manifolds and Rham Cohomology. So maybe next time you talk to a flat earther, tell them to study Rham Cohomology, okay? And then, sorry, Riemann surfaces. So we'll add the rigidity of complex numbers, and we can find that in 2 dimensions, geometry will become really strict in 2 dimensions, and the surface can be determined almost entirely by how many holes it has. So that's why Riemann surfaces are pretty powerful. And then we'll talk about the discretization of space into triangles to give us the math of singular homology. And this can help us just build a machine that can count how many holes in any dimension with integer precision. Okay, I've seen like this really cool Instagram video. I'll have to send it in the Discord, but yeah, it was really cool where they I think made like Peter Griffin's face out of like triangles or something. I don't know. And then sheaves and schemes. So we're gonna try to abstractify this a little bit. We're gonna realize, okay, because this is just something you think about when you're walking, to taking on a nature walk or something. You're gonna realize that points are overrated, okay, and you're gonna rebuild geometry entirely out of rings of functions. All right, cool. And this will unify geometry with number theory. All right. So points are just going to be this is the foundation of string theory, right? And points instead are just going to be like rings. Yeah, that's basically how you can think about it. And then vertex operators, algebras. Finally, we will just talk about space being replaced entirely by representation theory, and symmetry itself will create space. All right. So that's another thing. And this will give us the mathematics, really, of string theory and the Monstrous Moonshine, if you've ever heard of that. Um, if I'm not making any sense, I'll try my best to make this as intuitive as possible. But one thing, well, I guess one concept that you should really, if you get, oh god, that's my Discord. But if you really, I'm going to mute it, but if you really get one thing out of this, really, it should be the concept of cohomology. If you take nothing else from this chapter, just remember this one word, because it's the antagonist, and it is also the protagonist of modern geometry at the same time. So in calculus, you solve differential equations locally, okay? And I'm not going to get too much into this, but you can find a solution here in some little patch of space, right, in calculus. But the question is, can you extend that solution to the whole universe? And that's not an easy question to answer. We're not going to get into jet spaces or jet bundles today, but that's where this is headed. We're headed towards solving differential equations with all the mathematics that we have developed. But we're not going to do that today. We're just focused on the mathematical objects themselves and the operations. So, of course, usually the answer to extending solutions to the whole universe is usually no. And you'll hit like some kind of snag or paradox or a hole in the topology or whatever. Cohomology is essentially the mathematical measurement of that no. Okay, so if you can extend the solution to the whole universe, no. Okay, well, by how much? That's cohomology. Think about it like that. It's a language of obstruction. It measures the distance between local truth and global truth, and it tells you why we can't simply flatten the Earth onto a map without distorting it. Okay, so that's what this answers, and it's a central theme. All right, so let's leave the safety of linear algebra, and we're going to bend the world. Not physically, that would be kind of dangerous, but with our minds. Okay, so yeah, again, rubber sheet geometry. We're going to talk about something called a fundamental groupoid. All right, so we've abandoned really the metrics of chapter 1, right? In this section here, we're gonna define space using the minimum amount of information required to talk about continuity, right? And that's topology. We'll find that even without a ruler to measure distance, right, we can still detect the shape of the universe, and we can tell a sphere from a donut, not just by like measuring size, but by measuring their holes. And there's a way to do that, okay? And the oid part of the group just is a generalization to category theory. All right, so we defined again continuity using delta epsilon, and then of course our definition relies on distance, right? X minus y. But if we don't have a metric, we're working on a network graph or quantum states or string theory landscape, or distance is like this like fuzzy concept. We instead need a definition of space that relies only on containment. Okay, so what's contained in what? And topological space, X here, well, technically it's a pair, but a topological space X is equipped with a collection of subsets of X called open sets tau, and these must satisfy 3 axioms, where we have the trivial, the triviality of the topological space, which just means that the empty set and the whole set are in the tau. Okay, they're all in the open subsets. Okay, just open sets. Sorry. And then the infinite union, so you take an infinite number of sets, combine them, and the result is open. And then finite intersections. If you take a finite number of open sets and find their overlap, the result is open. We'll say a set is closed if its complement is open, and closed sets are closed under arbitrary intersections. So it's kind of like a negative definition of open. Okay. Continuity. A map is said to be continuous if the preimage of every open set is also open. All right, and then that's the advantageous. This is the advantage of using topology in this way. Here's some example topologies. So a standard topology just means, again, we can take the real number line, and this is usually how we do calculus, just with standard topology. And open sets are unions of open intervals. All right. We can have discrete topology, so every subset is open. Every map out of the space is continuous. All right. In discrete trivial topology, so if we have the empty set and the topological space, if they're both open, then only continuous maps into the space are constant. All right. If the domain is connected, remember connectedness. I don't think I defined it again, but yeah. We also have subspace topology. So if we have a subspace of the topology, open sets in A are the intersection of U, A and U for some U that's open in the topological space itself. Okay, so we can look at a subspace topology on the real number line, and this one's actually neither discrete, discrete or indiscrete. Because we have the it's approaching 0 here, but 0 is not included in the subset. So that's an interesting one to think about. There's also product topology. So if we have the product of two topological spaces, open sets are unions of products of those topological spaces with some U open in X and some V open in Y. And also the projection maps inherit the continuity here. Because it's just the preimage of every open set, and Y is open in X. So we could prove that. That's a fun proof. It's pretty easy. Quotient topology. So if we have the equivalence relation on X, and the quotient is this open sets whose preimages are under the projection are open in X. This is how we construct a lot of spaces, like circles, tori, projected spaces. All of this comes from quotient topology. All right. There's another one. It's called Zariski topology. I think we mentioned this in chapter 1 of the continuum analysis. But this is used in algebraic geometry. It just says that closed sets are the zeros of polynomials. And this topology is very coarse. So open sets become really huge. All right. So that's Zariski topology. Now, this definition of topology is really it's incredibly powerful because, again, it's coordinate free, so it captures the essence of like tearing. And if you tear a sheet of rubber, right, the points that were close become far apart, and the neighborhood structure would be destroyed. But topology really is just the study of properties that survive the stretching when you tear stuff. Okay, so let's look at the separation axioms. And I do define connectedness again. So, yeah, but without a metric, we can have weird points can clump together in really weird ways. You can impose these things called separation axioms to enforce distinctness. So there's the Kolmogorov separation axiom, which says that for any distinct x and y, there's an open set containing one but not the other. The Frechet axiom is that points are closed sets. All right. And then finite sets are also closed. So that's kind of an implication here. So the Zariski topology, for example, if we say closed sets are the zeros of polynomials, right? It would be in T1 here. All right. But it wouldn't respect the Hausdorff space, which means that distinct points have distinct neighborhoods. Disjoint neighborhoods, sorry. Okay. And I think we mentioned this as well in our previous handling of topology, just for what we needed for multivariable calculus. But yeah. There's also the regular plus C1. So regular topology plus C1, so it's a closed set. And a point outside can be separated by just disjoint unions. And there's also the normal, so +1. So disjoint closed sets can be separated by disjoint open sets. And then this is required for the Ursulon lemma, which allows us to construct bump functions or partitions of unity. These are very important for quantum mechanics and integration. So, for example, delta functions, right? Or what's the other one? The heavy side. Heavy side's the derivative, right? The delta function, or I don't remember, something like that. Or sorry. No, they're related by some derivative. I don't remember. But anyways, that's what Ursulon's lemma is. The bump functions or whatever, partitions of unity. We can construct delta functions, right? And distributions that look like that. So that's why this stuff is important, okay, for physics. You need topology for physics, right? Connectedness and path connectedness. So space X is said to be connected if it cannot be written as a union of two disjoint non-empty sets. Also, wait, before I move on, I just remembered something. The Hausdorff axiom. What's really important about the Hausdorff axiom? I just remember this, but it prevents pathology. This definition is very flexible. Well, the definition of topology is very flexible. But again, without distance, right? As we said, the clumping of points, right? Where did I talk about this? I don't remember. Oh yeah, they might clump together. But you can have sequences that converge to two different limits simultaneously, right? So to fix this, you need to say, like, again, for any distinct points x and y, I can find disjoint open little bubbles, right, that separate them. And then if a space is not Hausdorff, the world where the points can't be distinguished, right, is basically a ghost world. All right, and in physics, it's almost every manifold we care about is Hausdorff. So this is kind of a metaphysical consequence as well, because like it's assumed to be Hausdorff because we need reality to be distinct, if that makes any sense, right? So for example, you know what, I'll just leave that as that. But there's a relationship between Hausdorff spaces and like music theory as well, because fun fact, I used to be a music major. I started I liked the theory classes, but I hated practicing. But then I switched to physics. But yeah, anyways, that's some other. My original interest in topology was for music because of Hausdorff spaces. But I'll get into that later. We can. There's too much stuff to talk about. I need to move on. So compactness and finiteness in disguise. Compactness generalizes the notion of being closed and bounded, right? And again, this just prevents the mathematical objects from escaping to infinity or leaking out, right? So this is really a very misunderstood concept, because in Euclidean space, if we say a set is compact, if it's closed and open but bounded, bounded usually requires like a ruler, right? So how do we define smallness, without a metric? And what we have to do that is with information, okay? So a space X is said to be compact if for every possible open cover, and an open cover is an infinite collection of open sets that covers the entire topological space X, you can select a finite cover. All right, and that would be said. That's what compact is. And you can think about this. Of course, here's the direct translation. If you cover the space with infinitely many patches, you can throw away all but a finite number and still cover the space. So think about this. You're trying to spy on the space. Okay, I'm a flat earther, right? And I'm going to place an infinite number of cameras, right, or open sets to cover every inch of the space that I'm on the Earth, right? If the space is compact, you can turn off all but a finite number of those cameras and still see everything. Okay. And compactness then would mean the space doesn't have infinite complexity or infinite extent, right? It won't leak out to infinity. And this is crucial for physics because it guarantees that functions then will attain maximums and minimums, or the extreme value theorem. And we covered that, I think, in chapter 1, but this will guarantee, again, that a lowest state will actually exist or something. So compactness is a very, very important thing to understand. But I'm getting ahead of myself. So key theorems are the Hein-Borel theorem. So a subset of R in dimensions is compact if and only if it is closed and bounded. Oh, I'm sorry. And by the way, about the flat Earth thing, I was just trying to say that for views, I guess. I don't know. I don't know where I was going with that. But extreme value theorem. So a continuous real function on a compact space attains a maximum and minimum. And then Tychonoff's theorem. The product of any collection of open compact spaces is compact in Zermelo Frankel set theory with choice. Okay, and this is essential for defining Tychonoff's theorem. Allows us to define path integrals and measures. Okay, on finite infinite dimensional spaces. This justifies compactification in physics, and so we would say the interval from 0 to 1 is compact because any open cover has a finite subcover by Lebesgue number theorem, or number lemma, or directly. And this one does not, right? Because we're not including the endpoints. And so there's no way to cover it by 1 over n and 1 minus 1 over n because it has no finite subcover. If that makes any sense. We did like a convex, I guess, parametrization of this interval by 1 over n and then 1 minus 1 over n. Okay. So that's what that is. Again, there's no way to find a finite subcover. Now let's talk about homotopy, okay, and the fundamental group. We define the space. How do we characterize it now? We can't just measure volume. A beach ball and the Earth are topologically the same, right? A sphere. So, it doesn't matter what the volume is between the Earth or a sphere. They're still the same, like, mostly. I mean, the Earth is kind of a sphere, right? But approximately, right? And then a mug, right? Coffee mug and donut. That's the famous example, right? A torus has a hole in it, so does a mug. They're topologically the same, But how do we tell the sphere from the torus, right? We're gonna look for holes. So again, to find a hole, we can try to like lasso a hole. Okay, if that makes sense. So that's what homotopy is. We're gonna first, we're gonna first pick a base point. All right. Well, first we're gonna define two paths, gamma 0 and gamma 1. And they're gonna go from 0 to 1, and they map to the topological space, and they have the same endpoints. We say the paths are homotopic if one can be continuously deformed into the other. All right, so formally there exists, some map, right, for these two gammas onto the topological space, such that if we take some parameter 0 to 1, and then some s parameter that goes to 1. These are endpoints for all fixed t. And these endpoints here, homotopy is an equivalence relation. Okay? And what we will do is essentially, after defining these lasso parameters, we're going to pick a base point. So consider the set of all loops. All possible loops starting from and ending at x naught. Okay? We say two loops are equivalent or homotopic if we can continuously deform one loop into the other loop without breaking it. So on a sphere, you can take any loop and shrink it down to a single point. Okay, that's what this is. But essentially, this allows us to find something called the group structure of the topology. So with this, for the set of all the loops modulo homotopy, this set pi sub 1 is a map of the topology, or the group structure is a function, sorry, of the topology and that base point that we're at. And concatenation, again, is like this operation, or is defined from these operations here, which means that I can traverse gamma, then traverse delta, and reparameterize these, operations of the group structure. I also have the identity, so the constant loop is just the base point. It's equivalent to the base point. And the inverse is the loop traversed backwards. So there's inherent like directionality in the path, right? So that's kind of another thing to think of. But yeah, so again, pi 1 is a group. The identity, constant loop, inverse, reverse, and associativity. So again, on a sphere, or any loop in RD can be shrunk to a point, right? So that's a trivial. On a sphere, you can take any loop and shrink it down to a single point, and it'll slip off the back of the sphere. So the loop is trivial. That means it's simply connected. It implies simply connected. And then for a circle, for a torus, I didn't really talk about a torus, did I? Well, okay. For a circle, the loop will wind around the circle n times, and the integer n is the winding number, or the degree. And so the map, right, of the winding number would just be 1 over 2 pi I, integrated over the path of d over dt, or of dz over d. And that'll give the integer. All right. My computer's about to die. Hold on. But yeah, so now we have something that allows us to have a nice defined functionality, right? So a continuous base map, again, from some topological space with a base point to another topological space with another base point. This gives us something called a group homomorphism. So this implies then that we can have homotopic maps between things, which they induce the same homomorphism. Okay. Now let's look at again. Let's look at something called the Van Kampen theorem, which means that first of all, there's a problem, which is that the group structure is really hard to calculate. So this allows us to compute it by decomposing space. It's like a computational trick. So let's say if we have the topological space, and we want it to be defined as a union between some u and v, where u and v and the intersection between u and v are path connected open sets containing the base point. All right. So we could then say that we can define pi sub 1 as the amalgamated free product of just a group structure from both of these guys, okay, from both of those subspaces over the intersection of those subspaces. So, well, there's a lot. This amalgamated free product is isomorphic to just a group structure of these guys sandwiching this generator, okay, the generators from U and V, and that's cool. Okay, so that's the Van Kampen theorem. Again, it just allows us to compute it allows us to decompose space into smaller pieces, all right, that overlap. So we find the overlapping thing, and then in between them, that's where the that's the group structure at that base point, right? All right, the figure eight. So we can look at the figure eight topology if we just say let this be a left circle, right, plus a little of the right, and then of course the group structure U would be isomorphic to the integers. Let it's just a winding number, right? Let V be the right circle, generated by some B. Then the intersection is a contractible X shape, and so we get then that the group structure of the intersection is 0. So the result is the topology of the figure 8 is just isomorphic to the integers with the generators from these guys generated by A and B, which is isomorphic to something we call the free group of two generators, where A times B is not equal to B times A, and the loops do not commute. The torus, we can draw a loop through essentially a central hole. So that's kind of like the idea, and you can't shrink it and it'll get like snagged. So the fundamental domain square with opposite sides is identified, and you can just use the Van Kampen theorem on some suitable U and V on a torus to show that the group structure of it is just the integers. It's just the product of the integers. Okay. There's also a genus G surface. So a 4G G-gon, or a 4G G-gon is identified with, of course, these generators here with A1 times B1 times the inverse of these, and again the Van Kampen, we can just identify this as products. Again, we can just view this as products of the amalgamated free product to give us the state, or the bilinear kind of, or multilinear map between this. So this is just to show that you can use the Van Kampen theorem computationally. All right, and allows you to it's useful. All right, let's look at covering spaces. So there's a link between the fundamental group and unrolling a space. So if we have a covering space to just be a map, right, from some E, right, so covering space is a map P that is defined by E onto the topological space. That is continuous, it is surjective, it's locally trivial. That means that X has a neighborhood U with the inverse image of U to be isomorphic to U and F, where F is some discrete structure, or some discrete space. So we then define something called the fiber of the inverse image of X is some discrete set of points. Okay. So again, the covering space is the map onto the topological space, and if we want essentially to find from that cover space, if we want to find the fiber, we would take the inverse of something in that covering space, or something from that map. We take the inverse map basically, okay? Because it's topologically continuous. So something called the universal cover, X tilde, or sorry, is that a tilde? I can't tell, but the largest covering space is simply connected, so the group structure is 0. All right. If we look at a circle, let's look at the map, right, from the real numbers to the circle that is given by T maps to e to the 2i pi t, right, where T is the parameterization. The real line then is the universal cover of the circle. It will unroll the periodic structure, even though it's real numbers, right? So the integers act on the real numbers by translation, right? So t plus n. And so its action corresponds exactly to the group structure, all right, of pi of s1, all right? So if you look at the double cover of a circle, then what that means is that essentially after we traverse, essentially the double cover of a circle is a particular map that defines us going from the circle or from the topology of the circle to it's a map onto itself, right? So yeah, it's kind of like, I mean, you can kind of think about this idea almost as like a linear operator, except for topologies, right? So cover or covering spaces, they're just it's the same thing. We're just creating a homeomorphism. So anyways, the universal cover of figure 8 then is a infinite 3-valent tree, Cayley graph of the free, what's it called? I forgot, the free group. No, sorry, not the free group of God. I'm sorry, I'm bad at topology. I'm still learning this stuff too. But these are my notes, okay? And it was the free group. Yeah, it was the free group. I'm tripping. But yeah, so I honestly haven't really looked too much into this, but it's a cool example. So another one is the real projective plane. So this is obtained like as a disk of antipodal boundary identification, or the circle, essentially, with antipodal points identified. I'm sorry, not the circle, the two-sphere, which is antipodal points identified. So if we have the double cover, right, of two-sphere, right, or the cover of the two-sphere, we can map it to something called the real projective plane. And what that allows us to do is describe the fundamental group of this mapping, right? For path-connected, locally path-connected topological space, covering spaces correspond to conjugacy classes of the subgroups of the fundamental group. Okay, so subgroups of the fundamental groups, and the universal covers corresponds to the trivial subgroup, right? Another idea is called the monodromy action. This means that lifting paths are uniquely determines something called deck transformations. These are automorphisms of the cover. Okay, so this is another monodromy action we can also use. Okay, so the group structure, really, if you take away anything from that, it's probably just the group structure. This is the first instance of algebraic topology. We've converted really a geometric problem of like holes, right? I mean, a way to identify holes into an algebraic problem, which is groups. All right. Now the next thing we're going to talk about is manifolds and Rham cohomology. So we successfully covered the rubber sheet world of topology, and we can now stretch, twist, and deform space and calculate, fundamental groups, groupoids, if you will, and detect holes using loops. But there is a problem because topology itself is jagged. It allows corners, cusps, fractals, and you cannot define a velocity, right, at a sharp corner. So you also can't define gradients, right, on some like fractal or non-differentiable function. So to do physics or describe general relativity or electromagnetism or gauge theory, you need calculus. So what we're going to do is restore the concept of differentiability and bring that to topology. So let's describe something called a smooth manifold. A manifold is essentially a space that is indistinguishable from flat Euclidean space in dimensions. So if you zoom in far enough onto like some local patch of space, it's like kind of an ant standing on a beach ball. it'll look flat to the ant, right? Or us, on the surface of the earth. It looks flat everywhere, right? And this would allow us to perform calculus intrinsically, so we can differentiate functions or flow along vector fields or integrate volumes without really ever needing to step outside of the universe itself, or we don't need to like step outside of the earth, to look at it, right? We can just perform calculus on the surface of the earth, essentially. So we're going to construct the machinery, really, of differential geometry, tangent vector, the differential form, and kind of like the algebraic measurement of holes, known as the Rham Cohomology. So a topological manifold, we need to define this first. So this is of dimension n. It is a second countable Hausdorff topological space where every point has a neighborhood homeomorphic to the open subset of Euclidean geometry in dimensions. Okay, so to do calculus, you need to coordinate these neighborhoods, right, smoothly. So you can think of Earth again. You can't map the entire Earth onto a flat sheet of paper without distorting it, right? But you can map small pieces of it perfectly. So if you're like an explorer and you want to map out a certain part of the Earth, like, you can do it. You just can't do you can't do the entire thing without, distorting the Earth, because it's 3 dimensions, not 2. So what we have to do is construct something called a chart. And a chart essentially is a pair. It's an ordered pair, and what it does is it's a small map of a neighborhood itself. Okay, so onto a single, really, it'll take the curved piece of some manifold on M, and it'll flatten it onto the real numbers, onto Euclidean space. So that's what a chart is. That's the definition of a chart. An atlas is just a collection of charts that covers the entire manifold. And a crucial requirement is something called compatibility. All right. And what that means is if there's 2 charts, right, if they overlap, right, let's say I'm a pirate or something and I want to map the Mediterranean, right, but there's also somebody who is in, I don't know, in ancient Samaria, I don't know, and wants to map the Suez to the Mediterranean or whatever. The Mediterranean Sea, parts of their Mediterranean Sea is going to overlap, right? So essentially when 2 charts overlap, say like, they just have to agree, right? So if you move from one map to the other, the transition function between them, right, which we'll denote as phi sub beta, composed with the inverse of phi sub alpha, they must be smooth or continuously differentiable. Okay, infinitely differentiable, and that'll ensure that there's a smoothness property of this space that we're constructing, not just the map. So that's smooth structure. Okay, so you can think of the example of a sphere. You can cover the sphere with 2 charts using stereographic projection. So we can go to the North Pole and kind of essentially just kind of shine a light down from the North Pole to the plane z equals 0, okay, where the coordinates are on Sn. So this is for any n-dimensional sphere. And then you can take another chart and project it from the South Pole using the same method. And what you can do is basically cover the entire, you can, by stereographic projection, you cover the entire sphere. Okay. There's also the real projective space. This is the space really of all lines passing through the origin. It's locally flat, but globally twisted. So we can take charts and the set of all these coordinates, right, where the coordinates are not equal to 0, and these are essentially lines, and we can take a map, right, to look at different ways to project that those the space of all those lines passing through the origin itself, and you just get like a compact smooth manifold of dimension n. Okay. The transitions in that real projective space are smooth and rational away from the zeros. You can also look at the n-torus. So a torus in n dimensions just kind of looks like a quotient by integer lattice, and the fundamental domain from 0 to 1, of course, to the n, right? So that's how many you would have, or how many products of those sets you would have to describe that n-dimensional torus. But opposite faces would be identified with each other as well. This essentially is, again, a quotient by an integer lattice. There's also Lie groups. So some groups in physics like SU2 or SO3, rotations in 3D space essentially are manifolds. Okay, so, or even just general linear groups as well. Okay, so their dimension is the dimension of their Lie algebra. So every Lie group is a smooth manifold, again, of dimension equal to the Lie algebra dimension, using local charts around identity, of course, using that exponential map that we talked about last time, or just their matrix entries themselves. Okay. Now, in classical vector calculus, a vector is an arrow connecting 2 points. But on a curved manifold, okay, you can't just draw an arrow between 2 points, because that arrow then would kind of like pierce through a surface and leave the universe, right? So again, like, it's hard to draw a vector on a surface of a sphere. So instead, we got to redefine what a vector is. A vector, in and of itself, is something that does something, okay, to functions. A vector, in and of itself, differentiates functions. So when we think about vectors this way, if we have a tangent vector at some point on the manifold, we can describe, again, what is the differential, what does it mean to differentiate something? It means to construct a special linear map that satisfies a Leibniz rule in the most general sense. That's what it means to differentiate anything. And so, it's just, we can define then a tangent vector as a machine that will differentiate functions. The tangent space is a collection of all possible directional derivatives at a point P. And then we can have that the tangent bundle in a local chart, given that the partial derivative operators form the basis for that tangent space. It would be the collection of all these spaces stitched together. And this is essentially the playground of Lagrangian mechanics, okay? Because coordinate vector fields will satisfy that the derivative over the x or the I indice coordinates with a j indice will give you a chronic or delta to form the basis, and any vector can be written as such. Okay, any single vector that's defined in terms of manifold, and we can shorthand the velocity, or sorry, the tangent vector, okay, in terms of just a functional of the coordinates, right? So the collection of all tangent spaces now, again, is the tangent bundle, and a bundle is always a manifold of dimension 2n, okay? Now, this leads us to tensor fields as well, because we can now describe contravariance and covariance and be able to mix them. And this also is shorthand for Einstein summation. All right, so because we've constructed, everything would be in terms of the tangent spaces instead of, and tangent bundles, instead of just like vectors in and of themselves, because we defined the tangent vector itself as a linear map given some points on manifolds. Okay. Now we need to integrate. Okay, so in vector calculus you integrate over fields, but vectors depend on coordinates, right? So if you stretch space or whatever, the vector will change length, right? What are the things that vectors need to satisfy? Is they need to be able to scale by something, and you should add them, right? That's it. But of course with some axioms. But again, the vectors have like a weird dependence on coordinates, right? If you stretch the space, the vector will change its length with the space. So we need the objects then that transform correctly under these coordinate changes with some Jacobian determinant factor. All right, and we're going to construct this. So we'll say a K form. A K differential form is a smooth section, okay, of an exterior bundle, and it is totally anti-symmetric multilinear map that eats K vector fields and spits out a function. So again, we covered the multilinear map last episode, and anti-symmetry as well for helping us describe symplectic forms. But these objects, really, differential forms are born to be integrated. Right? They automatically handle Jacobian factors when you change coordinates. So again, for example, like last time, a zero form would just be like a scalar, and then a one form would just be something that measures length or work, right? If you have some, again, you can think about it as like some contraction of some scalar with some along some line, right? So you're integrating along a line, that's a one form, right? A two form would be like integrating along flux, okay? So what is a flux through a vector field? And basically an in form would measure some kind of volume, or like hypervolume, right? Hyperdimensional volume. And there was the wedge rules that we covered last time, all right, for symplectic forms. And we're particularly interested in the anti-symmetric multilinear case here. So it's a little more general. But really, the operations that differential forms give us, especially in these tensored notation for contravariant and covariance, is that the wedge product will capture that geometry of exclusion, right? So if we have dx dy, that would be equal to negative dy dx, right? The anti-symmetry. And that allows us to build volume, again, from length. Because it takes, just to be able to span a volume, or span a little element of volume, or whatever, you need this conceptualization of higher dimensions, okay, for your bases. But usually you form this with just like areas, or bivectors, if you will. So anyways, the wedge product will combine a K form and an L form into a K plus L form. And this is how you would compute it. So again, we would have 1 over the factorial of K and L in general, of course, with the sine function. That would then give us how to essentially contract these indices. The exterior derivative, this is a little d, okay? So whenever you think of the exterior derivative in differential operators, you just have a little d. And on functions, zero forms, essentially we'll just have that the differential, that the exterior, or the differential operator acting on a scalar function, or in other words, the exterior derivative acting on a zero form, right? That's a function of a vector field, would just give us the vector field as a function of that zero form, okay? So you can see like this recursive relation here in the definition, which is really interesting because this allows us to unify the gradient, the curl, and the divergence into a master equation. And I'll show that in a second. But on K forms in general, so for some K or some n, whatever, this is the formula that we would get if we wanted to apply an exterior derivative on a K form. And this would be extended by Leibniz in antisymmetry. The fundamental theorem of exterior calculus would just say that the square of the exterior derivative is equal to 0. And this follows from symmetry of just mixed partial derivatives. So I take the derivative with respect to x in respect to y on a 0 form. It should also be the derivative of with respect to y in respect to x on the same differential form for that 0 form to actually exist. Okay, in order for it to actually exist, that has to be true. And if you twice differentiate it using symmetry of second partials, that will give you the exact solution. Okay, so essentially you can think of this as like, I don't know, a more generalized way to think about Laplace's equation. And so when we go through Stokes' theorem, we can basically just grand unify calculus because the forms transform correctly, and we can write down basically the most important theorem in integration theory. So we would say let M be an n manifold with boundary, and let omega be compactly supported n-1 form. Then if we integrate the n-1 form of the boundary, we can say that is equivalent to integrating throughout the volume of the exterior derivative of the n form. Okay, so we get some corollaries, which is the fundamental theorem of calculus. All right, here the manifold will be defined over the interval from A to B, with boundaries being b minus a. We have the classical Stokes, so we would say let A be some vector potential, or a 1 form, right? And curl as a 2 form. Then the line integral around the curve equals the surface integral of the curl. That's classical Stokes. You can also get divergence theorem. So for volume form, the volume of the divergence of some field corresponds to the exterior derivative of the field with flat. Again, we also covered the musical lowering and raising, but we can then integrate the exterior derivative over the volume, and this would yield. It really is just convenient notation. Okay, and it's kind of like a structure preserving map, but it yields that the integral of the divergence is equal to the flux. Okay, so that's all essentially what we're getting. Integral of divergence equal to the flux. Also, Green's theorem is just a 2D case of the classical Stokes. Okay, so we get all these corollaries, and the physics link between all of this is, first of all, now that we have the language, we can just say, well, this is the reason why charge is conserved. Is because of flux, right? It's the reason that flux works. Both of these things. That's really Stokes' theorem. But now that we have this language, we can say successfully now that the electromagnetic field is a 2 form in F, okay, or a 2 form F, and this is just kind of a strength curvature, or sorry, a strength energy strength kind of tensor-like object, but it's essentially just a 2 form. All right, and Maxwell's equations, half of Maxwell's equations are simply that the exterior derivative of this field strength tensor is equal to 0, and this is like just the Bianchi identity essentially, and what the Bianchi identity gives us is basically a generalized Ampere's and Gauss's law. Okay. And the potential then also is a 1 form, such that if we have, this should be the Lorentz force in the work energy theorem, pretty much. This gives us work energy theorem in Lorentz force. The potential, we have some potential in terms of this, then we can define that such as we can define a one form such as that the field strength tensor is equal to the exterior derivative of some field object. Okay. Now, if the Rham cohomology for the two form is not equal to 0, magnetic monopoles would be possible, and I'll cover what that is in a second. But I'm sorry I wrote this a little bit early. But yeah, I mean, that's also another thing that's possible. Okay. So we can then have some kind of criterion to justify magnetic monopoles, which we would then have in terms of quantizing charge by the integral class. Okay, so again, these are just special cases of this one geometric truth, right? So the Rham cohomology, we essentially are going to try to measure holes algebraically. And this is really the central theme of this entire chapter. So, we made it. It's about like an hour in, maybe. So we have the identity. The square of the exterior derivative is equal to 0. And this essentially implies that the image of D, so what is the image of D? If we were to operate on something, on a form, on an exact form, it is contained really in the kernel of D, of closed forms themselves. So a closed form, we would say ZK, is a form with the exterior derivative acting on omega, where it has no boundary, right? Locally it looks like a gradient, and it would be what we'd say curl free. Now, classifying the exact form of a boundary will then give us that omega is equal to some D sub eta, all right? And it is a gradient, essentially. So what that means is if space has a hole, you can have a field that locally has a gradient, but globally has no potential function, right? So let's look at the Rham cohomology. So what this does is it's a group that it measures the failure of closed forms to be exact. Okay, so the exactness of the form determines if there's a unique potential or not. Okay, so think of a magnetic field circling around a wire. You can think that the curl is 0 everywhere outside the wire, but the field is not a gradient because the angle is not a single valued function, right? So again, the Rham cohomology, we can define this in terms of the closed K-forms divided by the exact K-forms. And we measure the failure, right, of closed forms per exact forms, essentially. That's the way to think about this. The kernel of the exterior derivative acting on a certain K-form over the image of it in the K-1, all right, to ensure that continuity. So we can look at the Poincare lemma, which is that for some star-shaped domain, or just on Euclidean space, every closed form is, and by star I think it means Hodge star, but I'm not going to get into that here. But K is greater than 0 is said to be exact, and so the cohomology of the K form, right, as a function of the real numbers, is equal to the real numbers if K is equal to 0, and 0 if K is greater than 0. Okay, what that means physically, again, what that has a direct physical consequence, because in empty space, if the gradient or if the curl of the electric field is equal to 0, then we know that the electric field is defined as a gradient of a potential function. And if we look at the circle, okay, the 0 forms again would have a cohomology equal to R, but the 1 forms, if we considered an angle form of theta, locally the exterior derivative of theta assuming arctangent of y over x would be closed, and so the square of the exterior derivative squared of theta would be equal to 0. But guess what? Theta is not a single valued function on the whole circle, right? So it'll jump by 2 pi, and so 2 pi is not equal to 0. So if it were exact, so whenever we integrate it, right, the integral would be 0 by Stokes. So we know then that the theta is closed and it's not exact. So we get the result that the cohomology for one form on the circle is also the real numbers. Okay? And it's said to be closed but not exact. If we look at the sphere, then, if we extend this to the n sphere, we can then have that the cohomology of the K form on the n sphere is if K is equal to 0 or in general. Again, we got this special case. We're just going to extend this to a more general sense for in dimensions. The cohomology is the real numbers if K is equal to 0 and in. Otherwise, it's just 0. Okay, the cohomology is 0. Next, we can look at the torus. So we can also just say, well, independent closed one forms dx and dy on the fundamental domain are not exact. If you get a volume form that's closed, the integral will be 1. So if we want the cohomology for the torus on a 0 form and a 1 form and 2 form, it's either the real numbers or it can be the real numbers in 2 dimensions. Okay. We can also look at the genus, a genus surface, so just how many, genus G is just how many holes it has. The cohomology for a genus G group, genus G surface in general, in terms of something we define as alpha and beta cycles, it would be real numbers in 2G, or on a, this is particularly for a 1 form. For a 2 form, we would get just R, right? Just in general. So we, again, generalize this torus, right, as genus 1, and then this formula checks out, right? So the 1 form with genus 1 gives us the real numbers 2, okay? Gives us R2. So Mayer in Virasoro sequence then says that if we have a manifold and we partition it into submanifolds and take ensure that it's an interior cover, a long exact sequence would relate the cohomology of the manifold to the cohomology of the partitions, right, and the cohomology of the intersection of those partitions. All right. So also we can do functorality. Again, this has computational consequence, but functorality. So we can define a pullback, which allows us to descend to cohomology, given essentially that we can, category. We can generalize this to category theory, and the cohomology over some differential forms will give us an explicit relationship between manifolds themselves. Physics application. So again, I mentioned the monopole in the last little subsection, but this is exactly how Dirac discovered the quantization of electric charge. Nobody talks about this. But if a magnetic monopole exists, okay, the magnetic field F is a closed 2 form with non-zero flux through the sphere. And by Stokes' theorem, if F, this 2 form, this closed 2 form, were exact, F is equal to the exterior derivative of some vector potential, or some potential, right? Globally, the total flux would be equal to 0. In fact, the flux is not 0, means the vector potential cannot exist everywhere. It must have a singularity or be defined in patches. So the hole in the calculus enforces then the physicality of quantization. We need to quantize physics because of that. That's kind of why that works, because a non-zero flux, again, implies that the potential cannot be defined globally. There's no global potential. All right, so we can conclude here by just saying that we just place calculus on a curve stage. We define vectors as derivations, right? So instead of, we have generalized, or we have merged the idea of vectors or tangent spaces, right, and taking derivatives itself, right? So we call this idea just deviation. I'm sorry, derivations. Sorry, I'm tripping. But derivations, okay? And then we then have constructed differential forms, and we define them in terms of integrands. And cohomology then is the detector of topological defects itself. All right. But so far we've really just looked at generic smooth manifolds. So now we need to impose a much stricter structure. And so let's see what happens when we force our manifold to be even stricter, which is, you probably guessed it, to use complex numbers, okay, and employ Riemann Cauchy, is it Riemann Cauchy equations or whatever? Yeah, something like that. And holomorphy. All right. So now we're going to discover really that in 2 dimensions, geometry becomes really rigid, and the surface is determined, again, almost entirely by its topology, and fundamentally the genus of the topology, or the surface or of a manifold, is, and again, they're tangent surfaces, right? In general. So this will give us, we're going to discover how, essentially, how we've equipped our surfaces with smooth charts. Remember, if we can differentiate and integrate, but again, the geometry is really floppy. So we can take a smooth surface and bulge it, dent it, stretch it, as long as you don't tear it, right? The smooth structure will remain valid. But in real differential geometry, you can always modify a function locally using bump functions without affecting the rest of the universe. And so we now impose a complex structure, and we then will, this will give us the implication of how important genuses are as properties of these topological spaces. We demand that the transition maps between our charts, the transition, again, going back to the charts or the atlas that we have, there must be some way to make sure that they're not just smooth, but also holomorphic. Okay, so the transition maps between the charts must be holomorphic or complex differentiable. And again, this imposes the Cauchy-Riemann equations, and the results of this is rigidity. Because in the complex world there are no bump functions, if a function is holomorphic in a tiny neighborhood, its behavior there determines the behavior everywhere. And this is what we call analytic continuation. We talked about this a little bit in continuum analysis, so you can go review that video as well. But essentially, you can't change a part without changing a whole. Okay, you can't change a part of the structure that we've constructed in complex space without changing the entire thing. So this rigidity will forces the geometry to align perfectly with the topology, and in 2 dimensions, one complex dimension, a surface is guaranteed almost entirely by the number of holes, or its genus. Okay, and this is like a generalization of the poles and residues and all these things. Okay, so this section really will discover the crown jewel of 2-dimensional geometry, which is the universal, or the uniformization theorem. Okay, and it tells us that despite an infinite variety of shapes that a 2D surface can make, there are only 3 possible geometries in the entire universe. Okay, we have proven this with complex structure. So let's look at holomorphic charts first. So a Riemann surface, we will define as X, is a 1-dimensional complex manifold. This means X is a real 2-dimensional surface equipped with an atlas, where the transition maps are biholomorphic functions from the complex plane to the complex plane itself. All right, and so that's what this means. We then can describe the transition maps themselves as holomorphic, and the orientation then can be properly. We mentioned orientation once, but now we can really properly define the orientation, because every Riemann surface is going to be orientable. It means there's two sides to it, all right, in general. And the complex structure then induces a canonical orientation. So multiplication by I rotates all the tangent vectors by 90 degrees and it reverses orientation once. We also can have, the structure will give us conformal geometry, which just means that holomorphic map, or the holomorphic map itself, will preserve angles. It doesn't preserve lengths. So on a Riemann surface, you can say turn 90 degrees left, but you cannot say, walk 5 meters. Right? So let's look at the first thing, the Riemann sphere. This is a complex projective map. So in the complex plane, a point at infinity, let's say we have the complex plane with a union of some point at infinity, we can take a chart. Of just the complex numbers, and then take the point at infinity. So it would be the complex projective line, right? Instead of the real projective line, we're just using complex projective line at this coordinate of 1 over z, where w is 1 over z. And the transition map then is holomorphic on the complex conjugate space. So what that essentially tells us is this gives us really the simplest compact Riemann surface. If we look at the complex tori, you can first take the complex plane and glue it together using a lattice lambda. And what this gives us is a donut shape. However, the shape will depend on the parameter tau, okay? And a fat donut would then be holomorphically distinct from a skinny donut. And essentially this gives us our first idea of moduli space, okay? Because whatever lattice that we're constructing in the complex numbers, the quotient space itself, or the moduli space, essentially depends on this fat tori, or wherever the magnitude of this tau is, this will change exactly the complex structure that we're generating from it. And the fundamental parallelogram on opposite sides would be identified as well. We can also look at the upper half plane. This is simply just a set of complex numbers with positive imaginary part. And this is the domain of hyperbolic geometry. It is biholomorphic to the open unit disk via the Cayley transform. Okay, that's just a thing to that you can look up. We can look at the punctured plane. So if we take the complex numbers and just exclude 0, the universal cover, the complex numbers would be done via the exponential map quotiented by 2 pi I over the integers, or times the integers. All right. Now let's look at holomorphic and meromorphic functions. So how do we study these Riemann surfaces? We first need to study the functions that live on them. So we would then say a function is said to be holomorphic if it is holomorphic in every chart. All right. So a function between a topological space to the complex. Okay, and then we can also have a function that a topological space mapped to a complex projective line is meromorphic if it is holomorphic except for poles of finite order. And this can be found, via the Lorentz series in the finite principal part. All right, these are just things that you should probably familiarize yourself with. I'm just trying to get through everything and conceptually introduce things, and it's kind of your job to, look at what's interesting, right? So the whole point of these videos, I just want to be really clear. Treat these videos like, at least in the beginning, or this really is the last video that I'm doing on math, before I get into physics, but treat this video like the grocery store, just go and look for something that you think is interesting and, take what you want, and, use it, and yeah, just treat this like the grocery store. So, Liouville's theorem. This is a bounded holomorphic function on the entire complex plane. And when we consider this, the theorem states that this bounded holomorphic function on the entire complex plane is constant. And the corollary that follows is for any holomorphic function on a compact Riemann surface, this also should be constant. And so the global holomorphy of that function is a problem, because on a sphere or a torus, if you want a perfect function, the only one that exists is a boring constant number, right? So in order to get interesting geometry, you have to allow the functions to break. You must allow poles. And so this is the substrate of the entirety of so again, the corollary that follows from the Liouville's theorem is that, again, on a compact surface like a sphere or torus, you can't have a function that's perfect everywhere. You really have to allow the singularities, and the singularities to dictate the behavior of the functions, okay, or of interesting functions. Okay, so singularities give you the structure. Rationality. So a meromorphic function, again, is a function that is holomorphic everywhere except for a finite set of points where it goes to infinity, like 1 over z. Okay? And really, meromorphic functions on the sphere of the complex projective sphere, CP1, are exactly the rational functions and their ratios of polynomials. So, for example, these functions themselves are rational degree d, and d has zeros, and d poles counted with multiplicity. So to keep track of these functions, we use divisors. And divisors really are just kind of a formal sum of points with some like integer weights, right? And we might try to represent a function with like some poles or whatever, and a zero with, triple zero at p, double pole at something, single pole or whatever. And so that's essentially how we would determine a divisor, okay? And again, it has finitely many non-zero. So the degree then of the divisor would just be the sum of all the sum of the points, right? And essentially those points are, again, those poles, okay, to count the zeros and poles. Again, that would be the definition of the degree. The principal divisor then would, for a meromorphic function where the function is not equal to 0, is the divergence of f. And where, again, the ordering with respect to p, or the ordering of the point where it's greater than 0, for zeros is less than 0, right? And so this function allows us to describe the map here and dot that with the points themselves. All right, and so what this allows us to do is say, well, for the principal divisor, or for really any meromorphic function on a compact surface, the degree of the divergence is equal to 0. And that means, essentially, that the number of poles, or the number of zeros, equals the number of poles counted with multiplicity. All right? And essentially, this is called, again, the degree formula. Okay? It's referred to that as the degree formula. But for any meromorphic function on the compact surface, the total number of zeros equals the total number of poles. That's all this is saying. So nature demands balance. You cannot create a zero without creating a pole somewhere else on the Riemann surface. Okay? The canonical divisor is just the divisor of a meromorphic one form, like let's just say dz. Okay? For a meromorphic one form, the divergence of omega has degree 2g minus g with a canonical divisor class. And the again, it just depends on the genus of the surface. And the degree of the canonical divisor is 2g minus g. And this connects the zeros of calculus forms to the topology genus of the surface. Okay? This is really, really interesting stuff. I highly recommend you look up videos of this after you watched my video. But we can basically classify complex Riemann surfaces. Also, I need to start making a list of books. I haven't gotten around to it, but I think I'm going to try to make a progression of like books that you could, a reading list that you could follow along with these little with these kind of chill commentaries that I'm trying to make. So but yeah, I'll make sure that this gets done on the Discord eventually. I'm just kind of enjoying Christmas right now with family. But wow, the Discord just went off. So classification of compact Riemann surfaces. So a compact Riemann surface is classified up to a biholomorphism by its genus, where let's say G is equal to 0, that's a sphere. This is the only case then would be the Riemann sphere, and it's unique. If we look at the genus 1 and want to classify tori, the tau in the half plane describes the ellipticity, and these are called elliptic curves. Okay, so elliptic curves are essentially compact Riemann surfaces of complex tori, that where the tau is in the half plane. Okay, for the quotient space. Okay, that's an elliptic curve. Now, if we look at higher genuses, hyperbolic quotients then would be the half plane, quotiented by gamma, where gamma is something called the discrete torsion-free subgroup special, or PSL 2, R. All right. So this is I actually have no idea about this. I will have to study this, but I wrote it down. So that's just another thing. We can classify compact Riemann surfaces. Now, the uniformization, I keep saying uniformization. The uniformization theorem is just this grand unification of the most powerful theorem in two-dimensional geometry. It just states that despite the infinite variety of shapes that a surface can take, there's only 3 underlying geometric structures. And every simply connected Riemann surface is biholomorphic to exactly one of the following: the Riemann sphere of positive curvature, the complex plane of 0 curvature, this would be parabolic, okay, and the upper half plane of negative curvature, which is hyperbolic. And we can then have universal covers. So again, this classifies all surfaces by their universal cover. So every Riemann surface has a universal cover that's equal to at least one of these 3. Thus, we can just say that it's an isomorphism for some discrete group. Okay, whatever discrete group that we want to choose. Okay, so for the Riemann sphere with finite cyclic groups, we get a sphere with points that are identified. So the geometry really is just spherical and it's uniquely determined. For genus 1, it's covered again by the complex plane. The structure is determined by the lattice, okay, parameter tau, and again, elliptic curves. This gives us the essentially, yeah, I mean, it just gives us elliptic curves. And then the genus that's greater than 2 or greater than or equal to 2 is covered entirely by the upper half plane, and every surface with 2 or more holes naturally carries a hyperbolic metric of constant negative curvature, and gamma again, it's the fusion group. Okay. So again, this solves conformal geometry in dimension 2 completely. So we understand conformal geometry in 2 dimensions completely. And this is extremely shocking because it means that hyperbolic geometry is not just some exotic kind of exception, right? It is the standard rule for the universe of mathematical surfaces. And almost every surface is hyperbolic. Okay. Now let's look at moduli spaces and Teichmüller theory. So if the topology is fixed, say genus 2, how many different complex structures exist? Okay, we can then deform the shape, we can pinch the handles or widen them, and the space of all such possible shapes is called the moduli space. All right, so the Teichmüller space, TG, these are marked hyperbolic structures on a genus G surface, so with dimension 6G minus 6. The moduli space, again, tells us we quotient the Teichmüller space by the mapping class group. Okay? And what that allows us to do is say, well, genus 0 has no moduli, else for the same, right? Genus 1 gives us a modular curve. The space of tori is one-dimensional, and it's parameterized by tau. And what genus greater than or equal to 2 gives us is a space of structures. So the moduli space then has complex dimension of 3G minus G. So this space essentially is the playground of string theory. Because when string theorists, and also it's kind of the playground of elliptic cryptography. So this playground then of string theory, when string theorists say sum over all possible world sheets, they're integrating over this moduli space. All right. So, for example, if we want the moduli space with genus 1, this would just be the half plane quotiented by the fusion group, respectively, and the fundamental domain again. You can look this up, okay? But essentially, they're isomorphic to each other. So let's get on to the Riemann Hurwitz formula. So how do surfaces relate to each other? That's essentially what we're asking. And if I like wrap a rubber band around my finger, right? And said, but we're wrapping a surface around another surface. This is something we call branched covering. So essentially, we want how does topology change essentially when we map one surface to another? So if we take topological space, make a map to another topological space. If this is a holomorphic map of degree D, a D-sheeted covering with branching, again, ramification at points P, we then can say that for a holomorphic branch cover mapping from this topological space X to Y of degree D for a compact Riemann surface, okay? We essentially can have that first of all, the cover will look like a kind of a stack of pancakes, if that makes sense. We will relate the characteristic essentially 2 times the characteristic of f to be equal to the degree times 2 times the characteristic of y minus this. Or if we want this in genus form, we can have that 2 times the genus of x minus 2 would be equal to the degree times 2 times the genus of y minus 2 plus 1 minus the ramification minus 1. And this is just basically the number of sheets that come together at some single point. And this really relates the topology, again, of one big surface, x, to the small surface, y, and the branching, and the branching index, okay? This formula will explain why you cannot wrap a sphere around a torus without breaking it, okay? You literally cannot wrap a sphere around a torus. But if you can wrap a torus around a sphere if you pinch it in 4 places, okay? Topology constrains the algebra, essentially. And we can look at this. So, for degree 2, ramification at 4 points with the index being 2, the branching equals 4. So, again, the double cover of a sphere ramified at 4 points gives us essentially genus 1. Okay, so this will give us genus 1. Can a genus 2 surface cover a torus? And then, again, it's impossible. And the degree 3 cover of a sphere unramified, this is also impossible. Minimal branching required for higher genus. So it's like, okay, that got really kind of, I guess, abstract. It seems a little more pure math. But essentially, the formula is really physical because it's explaining why you can't wrap a sphere around a torus without breaking it, but you can wrap a torus around a sphere if you pitch it in 4 places. And we're showing that topology itself constrains the algebra. Okay? Every surface is a quotient of a sphere, plane, or hyperbolic plane. And the war between 3-dimensional geometries is over. Representation theory has won. Okay? And again, we'll introduce what this is. But we have essentially shown that this, the real topology with the topology itself, right? Because we know about how topology constrains the algebra, we can then now study singular homology and diagram chasing with category theory. And then category theory will then necessitate representation theory. But we can essentially discretize space into triangles and build a nice algebraic machine that counts holes in any dimension with integer precision. All right? And really, by solving dimension 2, we impose this rigidity, this chaos of topology, right, into spherical, Euclidean, and hyperbolic. And again, we were able to cheat because we relied on the magic of complex numbers, which only works in real 2 dimensions. And so yeah, what we need now is a machine that, well, again, this only works in 2 dimensions, right? So we need a machine or a tool that works in any dimension. We need to count holes in 3D, or 4D, or 100-dimensional spaces using nothing but integers. So now we need to discretize space, again, into triangles and try to construct a machine that counts holes in any dimension with integer precision. So we need to then have the integer blueprint of space. We essentially first have been hunting for holes, right? We looked in the first section with loops in the fundamental group. We tried lassoing the holes, okay, in the topology. But the loops are one-dimensional, and they can catch a hole in a donut, but they might slip right through a void like a sphere. Okay? So if they slip through the void inside a sphere, right, then the algebra of loops is non-abelian. All right, so A times B is not equal to B times A. Great. Think about that. the sphere itself has like a hole in it, right? Or there's a void inside of the sphere. And so if we can take loops and it's not abelian, which just means that the a times b times a doesn't equal each other, that makes it really hard to compute, right? So then what we used was differential forms into Rham Cohomology to measure the flux through the holes. And this was a really beautiful way of doing this, but it had a weakness because it required smoothness. And it used real numbers, so we couldn't see, I guess, the twisting, right? We couldn't see the torsion. It couldn't tell the difference between a cylinder and a Mobius strip, because you can't have half of a hole in calculus. So what we need here, is a theory that is universal. Okay, we need a theory that is universal, and it works on any space, smooth or jagged or fractal, that is dimensional, right? We can see in 2D, 3D, or 100 dimensions, whatever. And it also needs to be abelian, so it needs to be easy to compute, and it needs to be discrete and count with integers. Okay. And again, the Rham Cohomology is great, but it can't distinguish between like twisting spaces. All right. So what we're going to do now is talk about singular homology. This section really is going to be, we're going to go through the triumph of algebraic topology. We're going to replace geometric intuition with a rigid algebraic machine called something called a chain complex. And we will solve spatial problems by chasing elements, again, through diagrams, right? And from the category theory foundation that we had last chapter. So to do algebra on a space X, we first have to discretize it, but we don't want to force a rigid like grid into the discretization of it because, again, we're just in a topological space. So we need a flexible kind of continuous probe that we're going to call simplicies. All right, and the standard in simplex is the generalization of a triangle to in dimensions. All right, and it's called something called a convex hole, and essentially what a convex hole is if you have a bunch of points, right? The polygon, whatever that you draw around it, to enclose all of the points is the convex hole, basically. Okay, that's what that means. But the in simplex then would be a convex hole E1 to En in some Euclidean space in n+1 dimensions. Okay, and you can have a point, you can have a line segment. This would be a triangle. This would be a solid kind of tetrahedron. And a singular complex then would just be a simple continuous map sigma of the standard simplex onto the topological space. And again, in an in-simplex, a singular in-simplex in the space X is simply continuous, the map itself. And it'll take, again, the standard triangle and squash it into the space. And it can be folded and crumpled or degenerate. You know, I think I saw an Instagram video of like Peter Griffin's face or something, like with a simplex form. Like, this is really cool. I think you should go look at some of the, if you haven't seen the simplex, singular simplex videos, you should do that because it's really cool. But again, it can be folded, crumpled, or degenerate, and singular just means no smoothness is required. But now, really what we can do is something bold. We can treat these geometric shapes, right, as if they were algebraic variables. So we will form something, and again, for the ith face, right, we can restrict the face opposite vertex I to the opposite vertex I. That's another property of this map here. But the chain group is an element of this group is a formal sum. Okay, so it'll just be some, like, some coefficients. I don't know, 3 sigma 1, right, minus 2 sigma 2, whatever, 5 sigma 5, right, and it'll just be the chain complex itself. It's going to rely on the map of our in-simplex onto the topological space, and will form something called the free abelian group, generated by all possible singular in-simplicies. And this is a finite formal sum that allows us to do arithmetic with geometric shapes. And it is a valid mathematical object. So we've essentially turned geometric shapes themselves, this sigma 1 and sigma 2, from a mapping of simplexes on topological spaces into just arithmetic. Okay, so this is something we call a chain, and this allows us to do arithmetic again with geometry. So basically what this means here is 2 triangles minus 1 line gives us this valid mathematical object. So now we can define something called the boundary operator. So how do we define a whole algebraically? A whole is something with no boundary, right? That is itself not a boundary. So really, we need a formal boundary operator. And this is what simplicial algebra gives us. For a simplex, mapping, again, the standard simplex to the topology, the boundary d sub n is the alternating, del sub n is the alternating sum of its restrictions to its n minus 1 n-dimensional faces, extended linearly. And what that means is, if you have v hat here, that means omit vertex, the ith vertex. Okay, that's something to keep in mind as well. If you've ever seen, if you see v hat somewhere. But essentially, let's say we have the simplex where n equals 1. A path from A to B would then be defined as a boundary A minus B, end minus start, right? But if we want to look at a simplex where n is equal to 2, or a triangle, right? V1, V2, V0, V1, and V2 basically means the boundary here would be the vertex 1 and the vertex 2 minus the vertex 0, vertex 1, plus vertex 0 and vertex 1 as like an ordered pair. And this is an oriented perimeter. Okay? And the boundary operator, again, is kind of like a map, if you will, from basically just takes this in simplex right here, and what it does is it will spit out an alternating sum of its faces and peel off essentially the skin of the object. So the fundamental lemma here of homology then allows us to say that the boundary of a boundary is 0. So if we were to compose, the nth boundary with the n plus 1th boundary, that's always going to equal 0. And if you want to prove this, the proof is actually not that hard. If you take a double sum for every n minus 1 face that appears twice with opposite signs, the geometry will just cancel it, or like kind of telescopes, if you will, and it becomes an algebraic 0. Each computation So each n minus 1 face appears twice with opposite signs. And that's another way to show it. But yeah, I mean, what this basically says is if you take a solid tetrahedron, right, or we take a solid, simplex in general, its boundary is a hollow sphere of triangles. So the boundary of that hollow sphere is nothing. It has no edges and it's closed. Algebraically, everything cancels out, so the boundary operator squared is equal to 0. This allows us then to construct singular homology groups because the boundary operator squared is equal to 0. This gives us a crucial inclusion because the image of del n plus 1, or boundaries, right, is contained within the kernel of del n, or cycles. So cycles then are elements in the kernel, the chains with no boundaries. So they're like loops and closed surfaces, right? And then the boundaries are images, or they're elements in the image of del n plus 1. So these are chains that are filling of a higher dimensional shape. And the nth singular homology group is the quotient of essentially the cycles of the topology divided by the boundaries of the topology, which again is just the kernel of the operators. Now, if we see, and again, the operators are just topological mappings of the, I don't think I wrote it out, but essentially the boundary operator just takes the continuous topologies in N and maps it into the N minus 1, essentially. It takes an N simplex and spits out an alternating sum, again, of those faces. So the nth singular, so what does this group tell us? Okay, I guess that's kind of the main question. What it tells us is exactly how many real holes exist. So we can take all the closed loops, again, or the cycles of that topology, and we can ignore the ones that are just boundaries of disks. Okay, so that's why we divide it out. And what's left is the topology itself. So the key computations here. Let's first go through the reduced homology though. So we can add augmentation for n equals 0. That means that two cycles then are homologous or homologous. I don't know how to say that honestly. I think it's homologous, but they're equal in the singular homology group, and they differ by a boundary. So again, if we did a line minus a triangle, that would be the boundary of tau. Then that they should be equal to each other, and they wrap around the same hole. Okay. Now, and again, these are intervals, right? So a basic fact also that we can look at is the nth homology group, or the 0th singular homology group, is isomorphic to the integer of the number of path components. So that's another thing we can use. As well as homology is uniquely characterized by a set of axioms, or uniqueness for ordinary theories. So homotopy invariance, homotopic maps induce same homomorphisms, long exact sequences. So for pairs, X and A, there's a long exact sequence. Excision, so we can cut out pieces. Dimension axioms for singular points, the 0th homology group at some point is equal to the integers, and the homology group at n of the point is equal to 0 for all n is greater than 0. And then additivity, again, we also have these for disjoint unions. And these 5 axioms give us the Eilenberg-Steenrod axioms. Okay, and homology is uniquely characterized by these set of axioms. So that's pretty important because it'll give us the sphere, again, where this 0th homology group is just the integers. This first homology group is just well, the first homology group would be 0, right? No loops. But the second homology group would be integers, which is 1 void. And so that's something that you could keep in mind, right? As long as we're just extending this out for the sphere in dimensions. But if we said n is equal to 2 or whatever, that would you can compute that is the n is equal to 2. The singular group would be, again, the integers. Okay, so that's nice. We can also look at the torus. Again, the torus is essentially the product of the 1 spheres, okay, or circles, right? So the torus would give us that the homology group would be the integers here. The first homology group would the first singular homology group would be the direct sum of the integers. So these are 2 independent loops, meridian and longitude, okay, for the torus that defines its singular homology. We can also have that the second homology group would be the n. So this is the whole surface that encloses a volume. For genus G surfaces in general, we get that for the first homology group would just be the integers in 2G dimensions, where G is the genus, and then the second homology group would just be the integers. The real projective plane that's non-orientable would give us the first homology group. Again, remember, this is non-orientable. So for H1, for the singular homology group of where n equals 1, we get Z2. This Z2 is something we call torsion. Okay, what this means is that we're doing the integers mod 2, and it says that if this tells us that if you go around the loop once, right, you're trapped. If you go around twice, you shrink the loop to 0. And the Rham Cohomology, which uses real numbers, cannot see this, but singular homology is able to see essentially the twist. Okay. So that's great. We can also look at the Klein bottle particularly, and this again gives us the loop around the singular homology group for the n equals 1 case, but also we get the twist, we get the torsion that we want. So for the Klein bottle, we look at SM wedge Sn, okay, where these are for the the spheres for m and n are greater than 1 or greater than or equal to 1, we will get in general, which is kind of interesting, that the singular homology is the real integers, real integers, just the integers. So if you decompose 2 hemispheres plus a cylinder, again, the Meyer-Bit torus will yield that the homology groups are both equal to the integers. We can also look at the Mobius strip, which we can map a cylinder of an antipodal map on the circle. It retracts to a circle, and that the homology group is equal to the integers as well. All right, so we get a lot of interesting information, and we get the concept, we get the torsion out of singular homology that the Rham Cohomology couldn't give us. Now, okay, we rarely compute homology from the definition because there's infinitely many singular simplicies. So instead, we use homological algebra to break the space into pieces, and then we glue the algebra back together. We use exact sequences. All right, so again, the long exact sequences would formally define this, but you know, if a space X is made of two pieces, again, the Virasoro sequence will connect their homologies. So again, here's a long exact sequence of a pair. We have the n plus 1 homology group going to the nth singular homology group going to the of A, right? Which then just gives us back the X homology, and then back to the or it kind of creates the full movement from the n plus 1 to the nth one. Okay. The Virasoro sequence then, of course, if we took, we can connect their homologies by looking at the intersection between U and V, and then just directly summing both of these homology groups, which then gives us just the singular homology there, and then we will get the nth minus 1 singular homology for the intersection. Okay, so this allows us to compute the homology of X from the known homology of simpler pieces U and V. And this long sequence works again from what we covered last time. The snake lemma, right? If we imagine the grid of groups, really, but first, before we get on to the snake lemma, if we want to connect homomorphism, this map creates lower dimensional cycles from higher dimensional boundaries, and what this allows us to do is imagine the grid of groups, and if you have exact rows, you can define a connecting homomorphism that snakes from row n down to row n minus 1. Okay, and that's essentially what we were doing here. And the map, the boundary, or the connecting homomorphism is magic, because we can take the cycle of the whole space X, and it tells you how it gets cut up when you separate U and V as the cover, essentially, of that entire manifold. It will convert the geometry or of the topology. It'll cover the geometry of the game into chasing elements, really, through a diagram. All right, and so the 5 lemma just follows from chasing, and we'll get given some commutative diagram. Then there exists a snake map for the kernel of gamma mapping to the co-kernel of alpha, connecting the kernels and co-kernels into long exact sequences. So again, from the commutative diagram, we can have exact rows and long sequence of kernels, co-kernels, connecting homomorphisms, and extend it out that we did with the snake lemma. Okay, now what does this allow us to do? For actually calculating, we're going to use cellular homology, or it's called CW completeness. And instead of using infinite singular simplicies, we can build this space out of a finite number of cells or disks. Okay. So we can say a CW complex is a space built by gluing cells along their boundaries, and by attaching cells, we can start with points, 0 cells, and they attach disks via maps on boundaries. And so I have no idea what's going on here, but that should be for the CW chain complex. Let me see what's going on here. Not sure, but anyways, so you can see that Cn to the CW of X, right, the chain complex of that topological space, be equal to the integers. This is what math BB is. to the number of n cells. So for a boundary map, let's say we have del, okay, for an n cell, e to the n over a, alpha, we can then define this boundary map in terms of the intervals here, in general, for alpha and beta, from the nth to the n plus 1, where the coefficient then that's defining the n cell is the degree of the attaching map on the sphere around beta. Alright. And if we look at a theorem, let's say the homology of CW really is isomorphic to the singular homology. Alright, so this allows us then to computationally do these the CW homology is isomorphic to the singular homology in general. We just construct cells instead by gluing disks along their boundaries. Okay, so again, the CW chain complex is pretty tiny. The boundary then, is just a matrix of integers. So for the complex plane, or for the complex projective plane, let's say CP2, for one cell, the structure is a 0 cell, and then the 1 cell would be the complex projective chain 1. Okay, 1 4 cell attached by something called a Hopf map degree 2 with no odd cells. The chain complex can go from 0, the integers, and then alternate 0 back to the integer, and then with a 2 boundary going back to the integers, and then back to 0, and then back to integers, and then back to 0. Right? And again, our boundaries were 0, 2, and 0. Okay? Singular homology is a nightmare for the complex projective plane, remember, but the CW homology is 3 lines of algebra. Again, we get that the homology, after computing this, is the 0th singular homology would just be the integers. The n equals 2 singular homology is z, and then the n equals 4 singular homology is 0, and we just compute this very simply by looking at the boundary map for n cells. Okay, so that's super great. The Hurwitz theorem is another one. So how does homology relate to homotopy? Okay, in other words, how does homology relate to the fundamental group or some homotopy groups? They're harder because they're not abelian, right? But for an n-1 connected space, so n is greater than or equal to 2, the Hurwitz map, which takes the homotopy of that space and maps it onto the homology, or the singular homology, this is considered an isomorphism. So for n-1 connected space, this homotopy is isomorphic to the homology. The first non-trivial homology group abelianizes, that's a new word, and equals homology. Alright? So this means that the first non-zero homotopy group is exactly the same as the first non-zero homology group. And if we want to conclude this, then homology is simply the abelianization of homotopy information, and thus the fundamental group remains the only non-abelian fundamental invariant. All right? So we've done it. We've converted a fuzzy, kind of flexible notion of shape, right, into a rigorous list of integers. So a sphere, we can now just call 1, 0, 1, right? Or in terms, they're singular homologies, right? Or the shape of a torus, right? That would be integers 1, 2, 1. Or a Klein bottle would be 1 plus torsion, 0, okay? So again, the torsion was from the modular integers. Okay, so just the integers mod 2. But still, topology really no longer is about visualization. It's now we have the tool of homological algebra. Okay, but there's a problem. We've been studying spaces of points, and in modern algebraic geometry and quantum mechanics, the points are often irrelevant or ill-defined, right? We don't really care about points. So what matters now are the functions. We're going to abandon points entirely, and we're going to build geometry out of rings. Okay, out of rings that are defined by additive operations on functions. Okay, where we're going to unify geometry with number theory. All right, and this is really the end game of mathematics. All right. So we've thoroughly reached a point at which we've gone through all the sections and assumed that space was this like fundamental object, and we started picking points and layered topology and functions on top of them. So we measured holes using the fundamental groups and groupoids, forms like the Rham cohomologies, and chains. All of these assume that space was built from honest points that are equipped with continuous or smooth functions. But now we're going to kind of invert the reality of the situation. So in modern math, specifically in algebraic geometry, one can come to the realization that functions are more fundamental than points. So instead of defining functions on a space, we start with a ring of functions. And what we can do then is hallucinate the space that they must live on. Okay? So when we do this, we create something called schemes. And schemes show that points are not coordinates, but they're actually all the points are prime ideals themselves, and functions do not exist really globally. They're kind of glued together in something that we call a sheaf. This kind of grand unifies mathematics in general. It swallows the entirety of differential geometry, complex analysis, and number theory into just one single machine. So the prime spectra and the Zariski topology allows us to really build space from algebra. So let's let A be a commutative ring. It could be like polynomials or integers. And we're going to define the spectrum A as a set of all prime ideals of that ring. And so that's how we would symbolically show this. But another thing that's implied is that a point in this Zariski topology is a point if and only if it is a prime ideal. Okay? Why prime ideals? Because in classical geometry, a point is where functions vanish. So if we have some, like, f of a as a function to be equal to 0, then f belongs to the kernel of the evaluation map. And that kernel is a maximal ideal. But Grothendieck went further. He included all prime ideals. And so, again, redefining the shape of this set, we can declare closed sets of the ideal for any ideal within this commutative ring with unit 1. And of course, we can think of the elements and of the functions that are within the ideals as functions, okay? And the ideals within the primes means that the function vanishes at the point P, right? So we can look at basic sets. The complement of a closed set would then just be the P that is not part of the function, which is equal to the spectrum of A at that function, okay, evaluated at that function. And A is, again, the localization of F and allows us to divide by F. Since the set where the function F does not vanish, this allows us to essentially define the shape of the closed sets. And again, VI is what? It's the set of all primes containing I. And the topology is very, very, very coarse because it doesn't separate points well. but it is really the only topology that can be defined using only algebra. So, and polynomial equations. So that is the key defining feature, and also the extraction of basic open sets from this, as well as our ability to stalk the point. So a local ring at a sub p, can define different topologies. So if we consider the spectrum of the integers, the points then on the Zariski topology are the prime numbers, or closed points, and the zero ideal, which is the generic point, and the closure zero of the whole space. The closed sets then would be finite points, or the whole space. The spectrum of the complex numbers on interval x at y, or we could say k with some k algebraically closed, this would be called the affine plane. And in the plane, the maximum ideals here correspond to classical points. And then of course we would get prime ideals for irreducible polynomials that then correspond to the whole irreducible curves. The generic point is a point that is everywhere else. We can also investigate the ring of dual numbers, okay? And the dual numbers are this essentially means that the only prime ideal is epsilon, and the space only has one point, but the function epsilon is not zero. Its square is zero, okay? So this is what we call a fuzzy point, and it is a point that remembers it has a tangent vector attached to it, even though there's no curve. This allows us to do calculus on spaces that don't even have points to form a line, okay? And that's essentially where nilpotent fuzz comes from. We can also have the spectrum of the integers mod the four integers, okay? So this will allow us to have a nilpotent part. Let me turn off my Discord. Allow us to have a nilpotent part with the square of with the square of the ideal to be equal to 0. But again, it's a connected one-point ideal. So here's some examples of some of the Zariski topology that we've defined. Now let's talk about schemes. Space really is not enough. We need functions, and we need a sheaf. So we'll call the sheaf something. So a pre-sheaf on F, a pre-sheaf F on the topology assigns to every open U in X an object, a pre-sheaf of U, a set, group, or ring called sections over U. Okay, so when we talked about sections of bundles, now we really are assigning a pre-sheaf over some function. Okay, and to every inclusion of some function within U, a restriction map we'll call rho UV allows us to construct a pre-sheaf map. So the pre-sheaf of this open sections, or sorry, of these open sections over U maps to the open sections over V, which are restriction maps. Okay. Now a pre-sheaf is said to be a sheaf if it satisfies the gluing axiom. So if the open sets equal the union over all of the individual open sets indexed, and it is an open cover, we have sections that are in the pre-sheaf that agree on overlaps. Okay. Then there exists a unique global section in the pre-sheaf restricting to each section. Okay. Now, if we look at the structure sheaf, again, using the gluing axiom on an affine scheme where we have the topology to be equal to the spectrum of a ring of prime ideals, we can define the structure sheaf such that on basic open sets, we have the structure sheaf that is then the closed set of the function to be equal to the ring A localized at that function and allowing division by f. All right? And essentially, the gluing axiom, what's important about understanding, or what's important to understand about that, is that if you have functions, again, defined on little patches, u sub I, and so they must agree on overlaps, so that we have, some initial, some fi is equal to fj on the intersection of those, the functions essentially must agree on the overlaps. So then there must be, a unique global function or section on the whole union. All right? Now, if we look at a manifold and we want the structure sheaf of U, which is an open set of the topology, to be continuously and infinitely differentiable. Okay? We can look at this and define something called a scheme. And the scheme is a locally ringed space that is locally isomorphic to the spectrum of a ring. An affine scheme is said to be isomorphic to the spectrum of A, and a projection scheme is constructed from graded rings, like the complex projective space, or the projection of set for graded set. Okay. What this then allows us to have is that affine schemes give us a relationship between the commutative rings, which generalizes contravariance. So if we look at a real projective, or if we just look at the projective line, given the spectrum of some k over a t, via t parameterized by 1 over u, on the intersection of these two of the intersection of these two closed sets, we can then have their spectrums to be glued together in that intersection. Okay? And the morphisms now also preserve sheaf structure, and so that allows us to essentially continue where we left off. Okay? So let's look at the check homology, and this measures the ability or the failure to glue. So central theme now turns to cohomology again. In schemes, we don't look for holes using loops. We're going to look for obstructions. So what you can do is try to build a local structure or a global structure, like a vector bundle or a potential field or something, and you're going to build it locally on small patches, U, okay? And you'll try to glue the patches together on overlaps, and then you'll check, essentially, if the gluing is consistent on triple overlaps, and this would form, essentially, a check complex, okay? So let's go back. Let's let U, calligraphic U, just be the open cover of X. We can define chain groups based on the intersections, remember? So our first chain will look like elements defined on the single set, which will be the product of the pre-sheaves, okay? And what we can also do is define the second chain, or the second group, or I guess technically its index is 1. Okay, so it's BC1. And these are elements defined on overlaps, or disagreement data, where we're defining this in terms of the pre-sheaf that depends on both. And then we would also look at the triple overlaps. The boundary operator then would be defined as the sections indexed by I sub j to be equal to Sj given U of j, or U of ij, minus Si given U of ij, okay? You get alternating signs for higher degrees as well. And by defining the boundary operator, you define the kernel of the boundary operator as collections of the sections, such that the sections on Si and Sj overlap. And by the sheaf axiom, we can glue them to a global section. So we could have, again, that the cohomology group of the topological space with its pre-sheaf should be equal to some gamma, okay? And we can also have the image of this boundary operator that we're defining as the differences that come from simple restrictions. So let's look at the pth check cohomology group, and what the check cohomology group gives us for the pth is that the open cover, right, or the check cohomology open cover is equal to the cohomology of the complex, and this allows us to limit over refinements and find a global check cohomology. Leigh-Ray's theorem tells us that if intersections are acyclic, the check gives us the true cohomology. So let's look at a physics example. If F is the sheaf of the electromagnetic potentials, and H1 is the global potential, H2 classifies bundles that cannot be trivialized, so the magnetic monopoles. Okay? And so, again, H1 will allow us to, so let's look at the check complex again. I didn't really define it here, but from the check cohomology group, you can think about them as allowing us to go from C1, right, the locality of the chain, and then going from here, doing the boundary operator on C2, on C1, to map to, or to push forward onto the, onto the overlaps. Then we can push forward again onto the triples. The operator, again, measures the difference between the sections. And so, again, what we can have is that the kernel are the local sections that agree perfectly, and they glue to form global sections. And the image of delta, or of the boundary operator, these sets of gluing, basically they're sets of gluing instructions, right, that are consistent on triples, but do not come from global objects. So again, in physics, then, H1 here, for H0 classifies the global potential, but H1 classifies line bundles. It'll tell you if your electromagnetic field has a twisted topology, okay? Alright, so check cohomology is just an approximation, but the real kind of definition comes from, again, homological algebra. So in order to understand the global section functor, we first need to look at the functor that is left exact. So we'll take we'll let gamma be the functor that takes the sheaf and returns global sections. And this functor would be said to be left exact. So from 0, we trace an arrow to F, then trace an arrow to G, then trace an arrow to H, and then to 0, right? This would give us the functor that takes the sheaves and does this, okay? However, this is not right exact, okay? The surjectivity on the sheaf level is called local surjectivity, does not imply global surjectivity. And so the obstructions will prevent lifting. Just because a map of sheaves is surjective locally on small open sets, that doesn't mean that it is surjective globally, because to lift a global section from here to there, again, you might hit an obstruction. So what we have to do is define the sheaf cohomology, which is the right-derived functor of the global sections. It precisely will measure the failure of global surjectivity, right? And so the boundary map, again, delta, what that would allow us to do is take a global section of C, or not of C, of F, and spit out the obstruction class in the homology itself, okay, or the homological group. So if the class is non-zero, you cannot lift the section, right? And that's simply how that would work. Now, we then can compute them with, and this is what we call injective resolution on the sheaf, and apply gamma to take the homology of the resulting complex here. Now, an important theorem that comes, or there's a couple of important theorems, but geometry really is determined here by what doesn't happen, which is the vanishing cohomology, right? So on an affine scheme, let's say we have a spectrum of our prime ideals. All higher cohomology vanishes, okay? So we would say this all vanishes for p is greater than 0, which means that it'll confirm our intuition that the affine space will have no holes and has no topological traps, and the obstructions are purely global phenomena from the Grothendieck's vanishing theorem, okay? And this is what we would say is a quasi-coherent sheaf, okay? So again, the affine space has no traps and it's local. Algebraic data can always be glued globally. Another interesting vanishing theorem is the Serre vanishing theorem. So for a projective variety, like any complex projective mapping, for a coherent sheaf F, the cohomology groups vanish sufficiently for a large twisting K. Okay. So the more twists, the cohomology groups vanish. All right. If we look at the projective line, what you can have is essentially that it would vanish outside ranges. Okay. Serre then says it's coherent on projective. Okay. So p equals 0 for p is large. All right. We can also look at the nodal curve. So consider the curve y squared is equal to x squared times x plus 1. This curve will cross itself at the origin, and that singularity prevents the structure sheaf from being standard. So h1 of the sheaf the base is not equal to 0, and the cohomology detects that the singularity, the failure to separate the two branches at the crossing, and so for non-separated cohomology, we then get that it's not 0 as well, and that it's failure to be normalized. Okay, and we can also look at the cuspidal curves, where we have y squared to be equal to x to the third or similar. Okay, and this also does have some interesting results. Okay, so I would definitely take a look at these and try to construct those global or those structure type sheaves. Okay, now last thing really that we'll do before we conclude this section, this part is probably the one that takes the most kind of mathematical maturity, but sheaf cohomology is kind of the ultimate theory because it swallows everything else. If you take a constant sheaf on the real numbers, you'll get singular cohomology or topology, and you get that isomorphism that we established earlier. if you take the sheaf of smooth forms, all right, and you would then get differential geometry in terms of the sheaf of smooth forms. If you look at complex geometry, really, if you would get complex geometry from the sheaf of holomorphic forms, and that's called Virasoro cohomology, or in other words, Hodge theory. This is what we usually call Hodge theory. Okay, and the Virasoro cohomology essentially generates complex geometry. So on complex manifolds, right, Virasoro represents holomorphic forms and Hodge forms for P, Q. We can also compare with Grothendieck vanishing theorems and stuff for singular de Rhams over the quotient spaces of the complex and real numbers, right? And also, what else does sheaf cohomology do? It gives us the structure sheaf, right? So for an arithmetic curve, we can get class field theory, or number theory, in other words. So for schemes, over the integers, we get arithmetic invariance, and this is used actually in the proof of Fermat's theorem. So sheaf cohomology generalizes to schemes in arithmetic, and it is truly the Rosetta Stone of geometry and all kinds of things. All right, so we have completed essentially this mutation. We've started from metric spaces, and we've moved to topological spaces, ended up in ring spaces, and now geometry is no longer about visual shapes. It's about the algebraic properties of rings and the cohomological obstructions to gluing them together. But or creating schemes, right? But there's one final layer that modern mathematics really has been, and this is more kind of contemporary. But in string theory, we don't just have rings of functions. We have rings of operators. And you can think about them as infinite dimensional symmetry. So we're going to replace the ring itself now with vertex operator algebras. So this is really where symmetry of the algebra itself will create the space, and then we'll kind of touch the edge of something called Monstrous Moonshine. So vertex operator algebras and conformal symmetry, I know it sounds kind of crazy to do this, but this is really the end of geometry itself, because space becomes something called representation. And I've hinted at this a little bit, but we're going to really see from the narrative that we built so far, and we're gonna stop all of mathematics, up to here. But we've really traversed finite dimensional geometry, complex manifolds, and the algebraic geometry of schemes. But now we really reach the frontier where string theory, conformal field theory, the concept of a point then becomes replaced by a loop or a closed string. And as the string moves through time, it sweeps out a tube. If it interacts, the tubes merge and split. And the geometry of these tubes is not governed by finite dimensional groups like rotations or translations, right? They're governed by infinite dimensional symmetry groups, the diffeomorphisms of the circle. And what this does is kind of break classical geometry, because you cannot describe this with manifolds or schemes alone. We need a structure that replaces space with representation theory. And this structure is the vertex operator algebras. And in this framework, distinction between algebra and geometry just completely dissolves entirely. The symmetry algebra itself replaces, it essentially creates the space, all right? So, again, this is the subject of interest of conformal field theory and string theory. But these are vertex operator algebras are the algebraic atomization of this in physics. Okay, so let's look at something called the Virasoro algebra, and this is kind of the spine. This is the spine of the theory. So remember that a Lie algebra is the tangent space of a Lie group. Okay, and for the group of smooth deformations on a circle, say S1, the Lie algebra is the Witt algebra, and it is generated by vector fields. Okay, and we can complexify the Lie algebra, right? But in quantum mechanics, symmetries can be realized projectively up to some arbitrary phase factor. And so it doesn't matter how exactly whatever phase I'm putting in front of my wave function still, will allow me to describe the state. You can think about like a sine curve, right? If I flip it by some phase 2 pi or 4 pi or whatever, the symmetries can still be realized. And so that creates something called the central extension. Okay? So, again, we consider diffeomorphisms on a circle. We complexify the Lie algebra, and it's called the Witt algebra, and we generate it with vector fields as such. Okay? Now, what this looks like is the central extension, and this result is known as the Virasoro algebra. So the unique up to isomorphisms of a non-trivial extension of the Witt algebra, this is called the Virasoro algebra, and the generators then, given some integers and the union of some C, where C is some central and it commutes with everything, the commutation relations would then look like this. Okay, and this equation really is the entire heartbeat of string theory. All right, the commutation of the vector fields that we have essentially gives us, again, I think the most poetic way to put it is the heartbeat of string theory, because these generators these are generators of conformal symmetry, right? And so what's happening is the L0 becomes the energy operator, okay? Is the generator of scaling and energy, and its eigenvalues are conformal weights of the states. And the central charge, a number, measures what we call the quantum anomaly, or the extent to which the scale invariance is broken by the vacuum energy, right? Or some 0-point energy. And so what this allows us to do is recover global transformations, okay, on the complex projective line. And positive C corresponds to local scale invariance, okay? And what we able, and you can think about, again, central charge, right? You can think about this number not really as an operator, but it just tells us, again, how much the scale invariance is broken. So if C is equal to 1, then you'll have something called a free boson, all right? Scale invariance is really important because, this would tell you a single string in flat space would give us a boson, a free boson. But if we look at C is equal to, again, C is equal to 1/2, we would get the Ising model, or ferromagnetism at the critical temperature. Okay? And if we look at C, the charge to be equal to 26, this becomes the critical dimension of bosonic string theory. All right? If C is wrong, usually the theory is inconsistent. All right? Now let's look at operator product operator product expansion. So in classical algebra, A times B is a well-defined element. In quantum field theory, operators become distributions. So the product of two fields at the same point then is divergent. We really need to study then what happens as they approach one another. And this is what we call the operator product expansion. So if we have, the product of two fields at a point to be equal, again, to the central, to be equal to the central charge, sum over all of the elements of the singular part and the regular part, which just contains, multiplication and then negative powers of z minus w, encode the interaction and the geometry of the two fields at that same point. And so what this allows us to do then is describe or derive a stress energy tensor from a conformal field theory with the stress tensor at z to be equal to, again, field with z to the negative n minus 2. This should interact with a primary field of weight h. And so when we look at their interactions, we can then get the pole of order 2 to measure the weight or energy of the field, and also a pole of order 1 to generate the translation. All right? And what this allows us to do then is define rigorously our mathematical way to expand operator products, okay, in distributions. Next, what we'll have is the vertex operator algebra axioms. So a vertex operator algebra is a vector space that encodes the state field correspondence. So what that essentially means, again, in classical physics, the reason why string theory is very interesting, or provides to us a very useful mathematical tool to understand classical physics from a different lens, is because if you have states, right, particles, and fields, or that encode forces, right, they are different things. But in vertex operator algebra, particles and fields become the exact same thing. Okay, so the state field correspondence principle states that for every quantum state within the vertex operator algebra, there exists a field operator, let's say y of a comma z, living on the Riemann surface. And again, the vertex, if we were to define this then, the vertex operator algebra is a graded vector space. So where we're taking the direct sum of all the vectors with conformal weights, equipped with a linear map, okay, where we have V that maps onto the endomorphism of V, and also taking the interval from Z to Z inverse. We can then define the vertex operator that takes the state, then ya comma z, and what it does is it's going to smear that state onto a field, okay? And so the vacuum state 1, okay, where we look at the vertex operator where a is equal to 1 comma z as the identity. So the vacuum state creates the identity operator, and the next axiom is that the creation would be the evaluation of the vertex operator at 0 to be equal to a, and this means that the operator will create the state from the vacuum itself, okay? And then the Virasoro element, okay, so that means that there exists a vector within the vertex operator algebra or this graded vector space, such that we have, when we take the vertex operator and use the Virasoro element, this would generate the algebra action on V. And this is typically just a kind of tensor that depends on the Z, okay? And again, it will generate the algebra on the action on V. And this will hence give us the fields at in for the Virasoro element in +1. We can also have the translation axiom, which allows us to encode essentially the symmetry preservation and show the algebraic method, of which the difference between them would be 0. Again, giving us that kind of geometric Noetherian symmetry conservation, just extended into the Virasoro algebra. And the other axiom is the Jacobi identity, which means that a massive algebraic identity that generalizes this Lie bracket will include a singular operator product expansion terms. And so this is what is known as Borchards' associator identities, right? So the associator, commutator-associator identities will then essentially give us, or be generated from the operator product expansion on that Lie bracket. Okay, and essentially, what did this do? What was the whole point of the map of the vertex operator? What it does is it takes a state, okay, and it smears it out into a field. And so the vacuum state, again, is this identity operator. And what this is called, the stress energy tensor, or again, when we create this state from the vacuum itself, we then can arrive from the Virasoro element at something, again, this is a stress energy tensor, but what it corresponds to is called the graviton state, okay, or the gravitational state. And so we can look at some operator expansions. So in quantum field theory, right, you can't multiply two fields, again, at the same point because it diverges. So again, we studied what happened to them. As they approach one another, and the singular terms then become the poles, again, encoded the geometry of the theory that we had. And so that's the whole point of trying to create the vertex operator algebra. Now, let's look at some master examples. We can look at the monster vertex operator algebra on V natural. And this means that if we have the dimension of some vertex operator algebra to be equal to 1 and V1 to be equal to 0, then we'll get that V2 is equal to 196,844 times 196,883 plus 1 from J. And the graded trace of this gives us a polynomial which encodes this vertex operator algebra. And it turns out that the automorphism of V natural from this musical notation gives us the monster group. And we covered musical isomorphisms in the previous episode. But essentially that's something that's really interesting, and this was discovered in 1988 as a consequence of the mathematicians and string theorists working hard on this type of physically motivated vertex algebra. Okay, lattice vertex operator algebras are interesting too, because even for unimodular lattices, so like E8 or Leach
Leech lattices. The charge itself becomes equal to the rank. And so theta series becomes like this partition. You can also look at more minimal models. So if we take P comma Q to be Koch prime is greater than or equal to 2, C, or the charge, should be equal to 1 minus 6 times P minus Q squared divided by P times Q. Okay, and this is an interesting model. And we can also look at the affine Kakamudi, which gives us Lie algebras that are generated. So we have the charge, we can have the charge in terms of the K, K times the dimension of the Lie algebra, quotiented by K and some H. Okay, so these are some examples, again, of vertex operator algebras at work. There's one book that I would reference just to kind of skim through, and that's essentially where I got these examples from. But I'm not like an expert in string theory. I'm not an expert in the mathematics of vertex operator algebras, but I am familiar with it. I've worked through a book. I'll be sure to add some references as well in some of the next coming videos, because I have gotten a lot of questions like, how do you learn all this stuff? What do you do to study this, and how are you able to put it all together and create like this narrative? And a lot of it turns out to just be, again, looking for really specific things, and kind of trying to figure out, the relationship between mathematics and physics in terms of its rigor. And that's kind of my guiding principle. And so I tend to do a lot of reading, a lot of looking through different specific parts of books, and trying to organize my notes and ask particular questions. If you want to learn more or want to, pursue this a little bit more seriously, I'm going to try my best to make some more resources for you guys to use, and make this little community that's passionate about these about physics and string theory and mathematics and whatever. You know what I'm saying? I personally am not super interested in string theory, but I think you cannot deny the importance of it and the development of the mathematical pursuit for something we call Monstrous Moonshine. Okay, so we've started from nothing, again, chapter 0, and we're ending here at basically the most famous unexpected result in modern mathematics. This is the most famous application of vertex operator algebras, and it unites group theory and modular forms. So essentially group theory and modular arithmetic. So there's something called the J function. And this J function is the fundamental invariant of the elliptic curves, or tori. And its Fourier expansion begins as this thing, okay? Where Q, of course, is going to depend on how we're encoding its phase with tau, okay? So that's the J function, okay? This function really is from number theory, and again, it equivalently maps elliptic curves in terms of tori. So the monster group, then, this is what we call the largest sporadic finite simple group, and it is really this kind of algebraic beast with 10 to the 52 elements, or 54 elements, and the smallest non-trivial representation has a dimension of 196, 883. Okay, and if you notice the coincidence here, the 196,884 is equal to 196,883 plus 1. This was the coefficient of the modular function of the dimension of the group representation, okay, plus a trivial scalar. And this coincidence here is the monstrous moonshine, and it implies a deep connection between the isometry of numbers or elliptic curves and the algebra of symmetries, or the monster group. So Borcherd's solution in 1992, he proved essentially that there exists a specific vertex operator algebra, the Moonshine module, V natural, such that, this is a natural representation of its musically isomorphic, such that its automorphism group, again, is the monster group. Its graded dimension is a partition function that is exactly equal to the J function minus 744. And again, that's the graded dimension. And how do we physically interpret this? Okay? Because again, this came from the vertex operator instantiation of what was needed to study physics. Well, string theory, again, provides that physical interpretation, or really, it's not it's kind of metaphysical. We're kind of in a weird spot here because we've constructed mathematics in this kind of mostly pure way, but we're at the end of mathematics, but it seems like we're really beginning at the start of physics, if it makes sense. So, it's kind of like a proto-physical interpretation, because of this mathematical algebraic structure that we've discovered. The monster group essentially is the symmetry of a bosonic string propagating, okay, on a 24-dimensional donut via the Leech lattice. Okay, so again, the monster group, again, is a symmetry group of bosonic string theory compacted on a 24-dimensional lattice, the Leech lattice, with a integer mod 2 twist. Okay, and then the Moonshine vertex operator algebra from the natural isomorphism has graded dimensions and twisted traces, something called the McKay-Thompson series, and the Hofmodulin for genus 0 groups. And what this does is connect the Leech lattice to the vertex operator algebra to monster automorphisms. And this J invariant graph will show poles at cusps and critical behavior. Okay? So, again, this is very interesting, and this has some consequences, because it's like, all right, well, this J function seems kind of important, but why does it matter? Because in string theory, we can compute physics by summing over all possible histories. In a closed string, we'll trace out a tube. So if we join the ends and make a loop, a vacuum fluctuation, then the surface becomes a torus of genus 1. Okay? And a torus then really is shaped by a parameter tau, and negative 1 over tau. They are geometrically kind of identical here because we're swapping latitude with longitude on the tori. But again, a fat torus and a skinny torus are often geometrically identical, and this is something that's called modular invariance. Okay, so for the theory really to make sense physically, the partition function should be the trace of the Virasoro algebra and of this quantity here that's in terms of the charge, and the 24-dimensional. We're normalizing by the 24 dimensions. It must be invariant under this modular group of SL, the special linear group over the integers, where its partition again is modular, must be a modular invariant, and this is a simple geometric constraint that is very, very powerful, because what it does is it forces the dimension of space-time to be 26 for bosons, or to be 10 for superstrings. And what this also does is force the central charge, C, to take specific discrete values. So the geometry itself is going to dictate the faces. Okay? It's going to dictate the physics. So we can look at for rational conformal field theories and vertex algebras. A torus partition can then just be the sum of the characteristics of this particular groups, of the particular tori. So we can just take the characteristics of the tori, and this also is invariant under SL, comma Z. And characters, again, are equal to their traces over the Riemann module, and the fundamental domain for the special linear group on integers is that the modulus of tau is greater than or equal to 1, and the real part of tau is less than or equal to 1/2. The Verlinde formula gives us a fusion operation that allows us also to describe the scattering matrix, or the S matrix. And this is also important for physics because it allows us to describe the interaction of high energy particles. So this conclusion, really, we have arrived at this very satisfying conclusion, because we started with topology of rubber sheets, right? And then we moved to smooth manifolds and differential forms. We constrained them with complex structure, and then we discretized them into homology groups. We then dissolved the points into rings and sheaves, and we looked at the hallucinated geometry of those dissolved points. And finally, we replaced space itself. Space itself is just an infinite dimensional representation of the Virasoro algebra. So that kind of concludes the entire story of mathematics so far. We have mastered geometry and representation theory, and we have the stage. Now we need the script, and we need to know how fields move, how particles interact, and how forces arrive. And so the next chapter, we're going to talk about action principles, okay? And we're going to talk about the laws of the universe from the principle of least action and go more in depth on Noether's theorem, okay, which we saw elements of it kind of come back, but and then we're going to try to talk about the path integral. And so as the path integral is a morphism, and as a principle of least action, it's more generalized. And so really the drama, if you will, is about to begin. But so thank you for sticking around, and I'll see you guys in the next video. Let me know if you have any questions, or if you find any thing that needs to get any errata that needs to be implemented, and I will add it to the Discord. Thank you.